Hello, everybody. We're going to start a chapter on electricity. These will probably be our last two chapters for the year. And of course, we can't talk about electricity without talking about Benjamin Franklin, right? And also a little history lesson because if it's not for Benjamin Franklin, we probably have a different America right now because we probably don't win the Revolutionary War without his diplomatic efforts in France in order to get the French Navy to block the British Navy from helping reinforce General Cornwallis and allowing George Washington to beat Cornwallis and effectively end the Revolutionary War. So Ben Franklin played a major role in that. And one of the reasons why he did play such a major role is because of the respect that he had, and mainly as a scientist. Obviously, he did a lot of work with electricity, but he was obviously a printer, a publisher, an inventor, a philosopher, politician, soldier, firefighter, all those things. So um, he was a pretty important guy. People say that he invented bifocals, glasses, but it was just the bifocal part of that. He invented glass harmonica, the Franklin stove, um, and all kinds of fun stuff. Now, the funny thing is he never patented any of his inventions. He didn't seek to make money off of his inventions. He thought science should be something that be shared, and so he did so freely um, with everybody. He actually was responsible for the first electrical circuit diagrams. He kind of had a theory that electricity flowed from positive to negative, and he didn't really know why. Unfortunately, we know that that is not true now. However, it was accepted for so long and so many diagrams were drawn the way Franklin started it that we continue to draw them that way today just to keep everybody on the same page. But it is not correct. Um, so that was kind of a fun little thing. And then, of course, there's the whole lightning and the flight and the kite thing. Um, but he did not fly his kite in the middle of a lightning storm. Um, Other people did and got electrocuted and died. But what he was doing was just proving to him that lightning was indeed electrical. And he actually was the first to make a lightning rod so as to draw electricity from a lightning bolt away from a house or a tree that you didn't want to have blown up. And so he actually did make money on that because he installed them on other houses, and so he did get paid for that particular thing. So anyway, um, kind of a important guy in terms of science and obviously the creation of our country. So um, let's talk a little bit about electricity, shall we? So actually, let me start with a different color here that you can actually see. Okay, so yeah, not working at all. There we go. So electricity. So electricity is the term given to a wide range of electrical phenomena, right? Um, but it does govern almost everything because we are talking about from the atomic level and actually inside the atom, there's electricity, right? There's electricity flowing through us as people, but there's also electricity flowing from and around every atom and every nucleus. And so that's kind of a major thing that electricity has to do with. Um, it's a lot of power, a lot of energy, especially when it's in the form of lightning. But there's a lot of things that go with electricity. And technically, what we're going to talk about is electrostatics. That's when electricity is quote unquote at rest. Okay. Because electrodynamics gets a little bit more complicated and it goes beyond the scope um, of this class. So we're going to talk about electric charges, right? We're going to talk about positives and negatives, which we should have no problems with. We're going to talk about electrical currents, okay, and how electricity flows from one point to another, and it creates light in a light bulb and things like that. Okay, so let's talk first about electrical forces. Well, we've already talked about gravitational forces, and we've talked about the fact that two masses might be attracted to each other, right? Electricity takes it a step further and says that like charges repel and opposite charges attract, right? We knew this, okay? Sorry, technical difficulties. There we go. All right. So that's one of the differences between the gravitational force and the electrical force is this whole idea that uh, there's different polarities of charge. There's not different polarities of gravity, right? There's just gravity, but there is different polarities of electrical charge, one positive and one negative. Okay. Now the electrical force is quite a bit stronger than the gravitational force. Okay. Now, the only difference is that most of the time, electrical forces deal with things that are very, very small, and so we don't maybe sense the strength of electrical forces like we do the gravitational force. Right? We're sticking to the Earth, and we notice that, whereas we might not be able to sense electrical force quite as much. Of course, if you play with electricity at all, you might sense electrical force a little bit, and in not a good way. So don't be sticking your any knives or anything into both sides of a socket. You can stick it in one side, okay, but don't stick it in both sides. All right. Um, in molecular terms or atomic terms, we're talking about positive charges being protons, negative charges being electrons, and neutrons have no charge. Right? They're neutral. Okay. Um, why then don't we notice if electrical charges are so much, or the electrical force is so much stronger than the gravitational force, why don't we notice it more often? Well, the main reason is because most things electrically have a neutral charge, right? They have an equal amount of positive and negatives within the molecule, right, or within the composition, and so they're not necessarily attracted to from one thing, right? The pages of the book and the desk that they're sitting on, they all have a neutral charge, excuse me, and so there is no attraction between them, right? There has to be opposite charges in order, or same charges in order for there to be um, some force between them. Okay, um, so that's one thing to keep in mind is most electrical force is in balance. Okay. Okay. So the next thing we want to talk about is let's talk a little bit more about the atom. Okay. So inside the atom, all right, in the nucleus, right, we have this is where the protons and the neutrons hang out, right? Now, this is not drawn to scale, but out here on the outside is where the electrons hang out. Okay, now in chemistry, hopefully you learned about what an ion is, and that's when a atom has a slightly imbalanced electrical charge, right? It might be slightly positive and might be slightly negative. And this is actually a good thing because it allows other atoms to be attracted to each other, right? So if one atom has a slightly positive charge, it can be attracted to another atom that has a slightly negative charge, and they will stay together and form a molecule. Well, that's kind of important. We need molecules, right, to build things. And this is kind of the underlying principle of chemistry that allows molecules, in fact, to be formed, right? And that bonding that happens there is very electrical in nature, right? Even though we call it a chemical bond, it actually has a lot to do with electricity. Okay, so the proton and the neutrons form the nucleus. All right, it's a positively charged nucleus, right? Because it's got protons and then neutrons that have no charge, right? All the electrons of all atoms are identical, right? Um, each electron has the same mass. Each electron has the same amount of charge. Okay. Um, protons are about 1,800 times more massive than electrons, right? They have 1,800 times more mass, right? Electrons are very, very small in mass, but they carry the same amount of charge. So think about that, right? One proton and one electron cancel each other out charge-wise, but mass-wise, it's not even close, right? Protons are way more massive, okay? A neutron is has a little bit more mass than a proton, right? And again, most atoms will have an equal amount of protons as electrons, and it could still have a net charge. It's a little off depending on the alignment of electrons, and you should have learned that in chemistry. Okay. So then the obvious question, I hope it's the obvious question, why don't electrons get sucked into the nucleus of the atom if like charges attract? Well, if you remember what we talked about with gravitational force, we have a moon orbiting the Earth. Why doesn't it get sucked in? Well, it's got a velocity, it's got a tangential velocity that keeps it in orbit, right? It keeps it from falling into the Earth, and instead it falls around the Earth. Kind of the same thing. Electrons are moving around that nucleus, and they're moving at a speed great enough to keep it out there in the outskirts of the atom, I guess we could say. I heard it once said that if we were to try to put this into perspective, imagine Yankee Stadium with a baseball at the middle of Yankee Stadium, and that's the proton, that's the nucleus, and electrons would be on the outer rim of Yankee Stadium, and they'd be the size of marbles. Okay, so that's how much space there is between the protons, the neutrons, and then the electrons, kind of working on the outside of that. Okay. Interestingly, the nucleus was first discovered inside atoms in 1911. Um, and we still can't see an atom or the nucleus of an atom, but through indirect observation, we can see the effects of atoms. Now, I kind of use the analogy of the moon orbiting the Earth. Well, obviously, an electron is a lot closer to the proton than the moon is to the Earth. Um, but there's some other forces involved, and we'll kind of talk about that um, a little bit later. Um, if it was just a similar gravitational thing, it would take about 100 millionth of a second for the electron to spiral into the nucleus. Okay. So we talk about the electron orbiting the nucleus, right? But that we actually talk about it in terms of a shell. Bohr's model, if you remember, had different layers, different shells around the nucleus, and so many electrons could what's the right word? Inhabit the first shell, and so many electrons could inhabit the second shell, and so on and so forth. Um, but there's a lot more to the nucleus than that, and the behavior between protons and electrons. But again, later on, if you decide to study chemistry in college, okay. Um, an electron, though, does behave like a wave, okay, and needs a certain amount of space in order to go through its wave-like behavior, okay. And it's also related to its wavelength, okay. And again, in later physics classes or chemistry classes, you don't you'll study that more. But know this, that the forces that keep electrons and neutrons, or let's say, sorry, protons and neutrons in the nucleus, and keeps electrons inside of an atom is called the nuclear force. Okay. And the nuclear force there's actually two forces within the nuclear force, but it's the strongest force in nature. Okay. And so you can learn about that a little bit later. All right. Now keep in mind, we talked about the fact that energy cannot be created or destroyed, right? Conservation of energy. Well, we also have the conservation of charge. Okay. So charge cannot be created nor destroyed. Okay. There always has to be a balancing of charge, right? Electrons can't be created. All right. But they can be transferred. Electrons can be transferred from one material to another. And that's the main underlying fundamental principle of electricity. Okay. Um, but we're going to actually stop right there, and we're going to pick this up on Monday and talk a little bit more about the conservation of charge and Coulomb's law, which you'll notice will be fairly familiar. And then we'll talk some more about electricity. So that's going to do it for today. And if you have any questions, I will see you tomorrow. Thanks.